Hello, and welcome to the part 8 of Hexagonal Multi-surface Pattern lesson in Grasshopper. In previous session, we mapped the pattern onto a surface and made few branches of mapping algorithms. Today we create a proper switches between the modes, check close geometry mapping, use reparameterization features of the Rhino itself instead of a 0 to 1 Grasshopper normalization, and learn the principles of surface reconstruction for more uniform pattern distributions. And the script, let me remind you, is meant to generate a seamless hexagonal pattern across multiple surfaces. Okay, so that's the script, how we left it off in the previous session. And as you can see, some things changed. Now, first things first, now all our modes are red, which is not good. We'll figure out in a second why it is the case, but before I would like to remind you that you can go into the description to this session and download this script at its current state. Okay, so in the previous lesson we constructed ourselves a surface in Rhino, streamed it into the Grasshopper, and then constructed ourselves a modes which are not really connected through the switch system, which we will do today. But right now we have a problem. Everything is red, and it's red because a surface is no more. Where the surface goes? Well, I actually never saved it. I mentioned it before briefly, and we will talk about that in the future, of course. But there is a relationship between Rhino and the Grasshopper, right? So when you create something in the Rhino and stream it into the Grasshopper, it will work. But if you save Grasshopper file but didn't do the same for the Rhino, it will disappear. So basically this is a new fresh Rhino file, and of course it tries to find a surface and it's no more. So if I'll bring the surface back in, of course it will work and everything goes back to normal. In the future lessons I will tell you how to properly, it's actually very simple, but basically how to properly save two files, because you need the Rhino file and you need the Grasshopper file, and both of them are supposed to be saved to work independently every single time when you open up a Grasshopper file. So let me now just quickly rebuild the surface, and I will remind you we use this node and in Rhino the tool and constructed the surface this way. It was just a planar surface, and because I constructed it clockwise, this direction become to be a U direction, and this one will become to be a V direction, which is not ideal. We need to flip it. So select the surface, type direction, click on the swap UV. This is basically everything we did before, and then right click, set one surface. All right, as you can see now everything works. So our main task for today is to construct the proper set of switches so that we can switch our modes. Depends on the settings, right? What kind of a mode we want to be used for mapping of a surface, right? So, and for that I will use the value list, the ones we used before, to create a list of switches. I will call it modes because I believe it makes a lot of sense. Right click, edit. So how many modes we have? 4. We have stretch, scale, U anisotropic, and V anisotropic stretches. So the first one, stretch. Now this one, I'll remind you, works properly when we are working in isotropic mode. So in the mode which basically shrunk all your pattern, all your 2D pattern into the square, and normalize it between 0 and 1, and then stretches to whatever aspect ratio the surface has. So it works only properly only for for isotropic surfaces, or isotropic grids, or isotropic mode. Okay, and that will be the first one. Let's type 0. The second one will be scale. I'll remind you the scale works for both for isotropic and anisotropic types of grids, so it doesn't matter for that. The third one will be U, and I will specify that it is anisotropic mode, or for anisotropic mode, where we stretch on U and we will follow, maintaining the proper proportions. And let's type isotropic, anisotropic, and V will be anisotropic also, right? Anisotropic. Okay, so the switch will be 0, 1, 2, and 3. Okay, So I have all our modes as a switches. Now let's construct a filter. So type filter. This we already did it before, so I hope you remember. I will plug the modes into the gate, and by default it will take the first mode, which is a stretch. Now to visualize the stretch, we will go in right here, change it to isotropic flat top, or that still didn't isotropic. The same mistake as in the previous lesson. So to the isotropic flat top or isotropic pointy top, I'll switch in the first one. And right now we are working in the wrong mode. So let me go in, plug the current one. This was our stretch to the stream 0, plug that into our grid. And as you can see, we have an issue. So it's not working properly. Why? Well, because a part of this mode and these settings, we need another one which will define the type of a parameterization of a surface. Now, in general, for now, we have two. One of them is normalized, and another one is whatever Rhino brings us, right? For the stretch mode, we need to normalize our domains. For everything else, we do not. So we need to create another switch. Let's go in, and I'll type another filter here. Now, our gate will be the same. So like this. And now, as we need 4 different modes, because we have 4 different options, because we have 4 different modes, we need to do some modifications. So by default, let's assume that we will not change what comes from the Rhino. So whatever Rhino's domain is, like 0 to 20, 0 to 10, let it pass. So we're passing it through. Let me just kind of do it like this. Just organize it a little bit to the right. So when we go to the stretch, we need to reparameterize this domain, basically normalize it, right? So I will use the node called surface. This is my pass-through node, if you remember. Specifying the type of data, right-click, reparameterize, and then plug it to correspondent input. So isotropic stretch takes the isotropic mode, the proper one, and the proper surface, which will go in and let me just do it like this. Like that. All right, makes sense. Okay, so that will be the stretch. And as you can see, it's already working, right? So we are in the stretch, isotropic. We're going to change the hex type from flat top to pointy top in the isotropic mode. As you can see, everything works like a charm. Okay, so for other modes, right from the get-go, we know that it's supposed to have the parameterization, which is not between 0 and 1, to maintain actual aspect ratios, right? For whatever we have. So I just take the current non-reparameterized surface, right? Remind you, this is the surface. Here it is. And then we just pass it through all the other modes, right? Let me delete this like this. Okay, these are out of the way. Let's now look at the next mode called scale. Right now, once again, we don't see anything because it's not plugged. It will be the input number 1. And this is our scale. And it's supposed to work. Let me see. Okay, what is the factor? Factor is 20. Looks like it's working. Yes, indeed, it's working. Now, why it's stretched? Because we are in the isotropic mode. If I will switch it to like anisotropic, it will not be stretched. It will be the proper one. And once again, we have an option to scale it, and I'll remind you to rotate it as well. We'll see the later examples when we will put everything to a test. Okay, so the next mode, the scale, works as well. Let's bring in another one and another one. So next two are interesting. The next two are U anisotropic and V anisotropic. So when we take the proper direction, stretch it, and then the correspondent proportion is supposed to follow. And the proper proportions are in anisotropic mode, anisotropic flat top and anisotropic pointy top. Let's switch on anisotropic flat top and see how we will map this and how we make the proper switches, right? So here are quite a few options. We have a flat top U, flat top V, pointy top U, and pointy top V. 1, 2, 3, 4, and we have only two inputs for U and V. So how we convert 4 to 2? Well, actually very simply. Remember that we have this switch, anisotropic flat top, pointy top, and then isotropic flat top and isotropic pointy top. They have numbers, gates 0, 1, 2, and 3. Now this one is 0, this one is 1. Let me remind you, this is the gate which we have here, and it is 0. So what I'm gonna do is I will use a filter here, and that will be my gate. I will organize everything in a bit. Just let me just kind of casually plug it right here, right? So the first mode will switch to U anisotropic. U anisotropic takes the U directions. We already have it, flat top U and pointy top U, right? So the gate from the original one describes the type, flat top or the pointy top, as well as the hex distributions at anisotropic or isotropic. So the first one will be flat, the second one will be pointy, right? So for the U, the first one will be flat top, this is the proper one, and the second one will be pointy, it's this one, so plug that in. And then we will take whatever it takes, and right now it is flat top anisotropic, and this is the stream number 0, here it is, we are working with that, and it will be aligned into the U anisotropic mode, work with the U anisotropic mode. This is number 2, plug that in. And let me hide this, and here it is, stretched on U, followed on V, perfectly. What's about the different orientation? So if I go to the hex type and switch it to pointy top, works like a charm. Now it tries to, once again, this is the flat top, it aligns to U. This is the pointy top, it still aligns to U, as you're gonna see, but the orientation of the hexagons is different. Perfect. Let's do another one, but this time for the V. So filter, stream filter, same gate, just the same gate. And now we have the combinations between flat top and pointy top, but V this time. So this is the, this is the stream 0 and stream 1. Right now it is 1 because it's pointy top, and I can plug that in to the last slot like this. And now if I'll switch that to V anisotropic, it perfectly matches on the V direction, right? U follows. And same will be with the flat top as well. Fantastic. So we now have all the modes we constructed, and they are switching, they can be switched using this mode and the actual type of a hexagon here. Okay, let's now organize it before we move on. So let me just select everything here, these, and these, delete. Let's try to make it less spaghetti, right? So probably take all of these ones, and it's just too big of a distance. Let's kind of shrunk them a little bit. Let's distribute. Let's distribute to the left or to the right. Which one will be better? I don't know. Actually, it's kind of shitty in all positions. Never mind. So let me take this one, line it a little bit. Let me take these. Oh, these ones, by the way, also are supposed to be here. Let me just do another notch like this. Okay, let's push that a little bit up. Maybe here a little bit better, no? No. Okay, I believe that's good enough. So let me just select everything here, turn it off. All right, so now we have the proper switches, and now what we're gonna do is we can look at the other aspects of our script. Now, if you remember, we of course has additional options, and one of them is the structure type. Now, for now, we mapped our pattern on a flat surface. But how about the closed geometry? We already have an option, and we even did it in completely flat representation, and it looks bizarre. Let's see how it works, and on top of that, learn about the reparameterization of the surfaces, because this is a very important part of the script also. So I will switch the mode to perspective, for example, like this. Let me zoom in. And let's now talk about the closed geometry. And for that, let's construct the closed geometry. Of course, there are multiple ways of doing that. You probably will be doing it outside of the Rhino, but as we are already in Rhino, let's do it. I will use the curve, this one, which is called the control point curve. And I will turn on grad snap off and construct a periodic curve. Basically, the curve which bites its tail, it's closed, and it's periodic. So let's do something like, I don't know, this. Like a blob, right? Let me click F10 to see the control points, and let's just do something like this, all right? Okay. Now I'm doing it intentionally, of course. Let me go into the top view, like this, and let's just make 2 points together, right? Like close, and these ones were like, you know, far away or something like this, like that, right? Okay. All right. So let's go back to the perspective. I will select the curve. I will type extrude curve, and just drag up somewhere, I don't know, somewhere here, and click. All right, so as you're gonna see, I have a new surface now. Now this surface is periodic, and if I will type what, you will notice that it is a periodic NURBS curve. It has a very specific domain, 0 to number, 0 to number. You know already where it comes from. We already discussed all of that. Now, this is a non-rational curve. It doesn't have a rationality because it's not a conic. And it has 7 control points. Now, this is, and the 7 control points in 3 degrees. So we have a couple spans here, indeed. Right. So if I will take this surface as it is and plug that into my script, well, let's see what will happen. So I will go in, I will just duplicate this curve, right click, surface, set one surface, and click on the surface, right? So we changed the surface now. Let me hide the original one and look at the curve. Okay, makes sense. So now let's go in and try to map our components or our values, our pattern onto the surface. And ideally, it's already supposed to work. So let's see what kind of a mode we have. We have V anisotropic. Let's switch that to U anisotropic, like this. And the anisotropic flat top, let them be anisotropic flat top, right? Okay, so now let's take the surface and just switch one and another, like this. And we have some results. Look at that. Quite interesting. Now, first and foremost, why it's so long? Why it's so, what the hell? Now, the two reasons why it is so long. First, of course, the domain, the actual mapping of the surface. We never checked that. You basically took what basically Rhino decided is a good idea. This is the first reason. The second reason is the nature of the hexagons themselves, because the hexagons in the flat top orientation will have these shape when you have the same amount of divisions, and you're supposed to have the same amount of divisions. So as you can see, it's elongated and wrapped around in a U direction, right? Now let's quickly check, is the U direction is the proper direction? Well, actually looks like so, but let's check. Select type dir for direction. Red goes to the right, yes, so this is the U direction, and vertical one is a green one, which means it is a V direction. Yeah, okay, it works correctly. So now let's look at our geometry, and we probably see some discrepancies. Now, first and foremost, you're going to see there is a gap. So this pattern doesn't want to bite its tail, right? It kind of supposed to, but it doesn't. Why? Well, because if we zoom in, we are in the open mode. It's for a non-closed geometry. Let's switch it now. Closed. Look at this. Something happened. Now we have a really oddly constructed connections which doesn't even look like a hexagon, right? Yes. Why it is the case? Well, let's go in and change the amount of divisions for our hexagons, and I will be moving it like 1, 2, and here we go. Now we have the proper amount of divisions. I will remind you why it is the case. When you look at the pattern in its 2D representation, we always have the connection, but depends on the staggered column. It can be skewed or it may not. And we decided that we will change this, the skewing, based on the amount of divisions on X if we are aligning in U direction, and using Y if we are aligning on V direction. And once again, by default, script aligns in a U direction, and we're going to change this not in the script, but in the orientation of a surface itself through the dir command. Okay. So let's go back and now look at our perspective mode. It looks great, but we don't have enough. Let's bump it up, right? So right click, edit. Let's say that the maximum value will be, I don't know, let's say 40, right? 40. Okay. Let's go here, edit, and we'll get 40 also. 40. Okay. Let's bump it up to 40, and let's say 36, I believe will be enough, right? Yeah, well, let's try 38. Okay, yeah, here it is. So 37, 36. Okay. All right, so now as you can see, it's completely closed, but there's some strangeness here, isn't it? Now, first of all, is this, it's just kind of right in your face. It's poking out. Why it's poking out? You're already supposed to know why, but I'll just want to remind you then when we are taking this pattern and wrapping it around, we're shifting all the column on one up for the right and for the left, so it will be consistent. And in some cases, of course, it will give you this one additional point which goes one up. In our case, it's absolutely not important because first of all, it goes far beyond the surface, and we will figure out how to chop it off because there are a lot of unwanted stuff. And of course, we can make this stuff even by adding additional rows. In our case, it will be on Y direction, right? Now, as you can see, it's perfectly matching. All right, so let's look at our pattern again and look at the distribution. Now I remind you that the anisotropic flat top is supposed to do a flat top hexagons, which is true. They are anisotropic, meaning that they're supposed to have the proper proportions within themselves, right? And the mode for a mapping is exactly the proper one on U direction, specifically for anisotropic. And yet, when you look at the pattern, I believe it's pretty obvious that some of the hexagons are relatively proper size and some of them completely squashed. What the hell? Right? Remind you that when I constructed it, I deliberately did it. So in the actual curve, if you see the curve, I put two control vertices very close together. And yes, of course, it's impacted the pattern. Let me explain why and what's more importantly, how to fix this. So let me go in and let me just gonna go in and construct another curve as a temporary curve. Okay, so this curve, right? This is a NURBS curve, and the NURBS curves, I'll remind you, are non-uniform rational B-splines. Well, they are not always rational, they can be non-rational, but what's more importantly, it is a non-uniform. What does it mean, this non-uniform? Non-uniform is not about parameterization. Parameterization can be uniform, we already talked this through. It can be choral, it can be uniform, there are a couple other options, depends on the system. But when we are talking about the description of the term that it is a NURBS curve, the non-uniformity is not about that. It's not about parameterization. It is the actual geometric distribution. Because if you have a numbers, for example, this is the start and the end, and we go from 0 to 1, the values are uniform 0, 0, 0, like 0 0.1, 0 0.2, 0 0.3, and so on and so forth, up to the last one. But the actual positions of these points, or sampling points, or t values on a curve, are not the same. They are not uniformly distributed. We can do that, but by default, this is the nature of that. That's what giving us an ability to create pinches, the acceleration points and deceleration points, and so on and so forth. Now, let me illustrate. I will go in and I will use this curve. Let me bring it. So I'll type curve, right click, set one curve. Now this curve is set. Now, if I will take this curve and I will reparameterize that, for example, from 0 to 1, because yes, you can reparameterize not only surfaces, but curves, of course. You already know why. It's the same geometric and parametric domain concepts. So if I'll take this, I can use the node which we used before, which called evaluate curve, right? To evaluate at a parameter. And the parameter, I will remind you, brought us by its domain, and the domain is the values between 0 and 1. Now, if I will plug the curve into the curve and I will plug parameter, for example, let's say 0.5, and plug it here, you're going to see that I have a point, right? But I'm specifying parameter manually. What if I want to specify between the values in 0 and 1? And that's we actually get to the tool which I wanted to explain in the second session, but actually explaining it only right now. The domain is a set of numbers. It's the bounds, but you never specify how many numbers they are. How many numbers between 0 and 1? We already talked about that. A lot of numbers in computers, a lot of numbers in mathematics, infinite amount of numbers. So we need to specify how many. Imagine that I want to have 10. How are we going to do that? Well, you already know, I believe, the node called series, where we start from 0. We're going to set the step like 0.1 and the count. Then we'll get ourselves manually 0 to 1. Or we're going to use, as we already know, domains, and this is our domain, we're going to use another node which sits under the sets, sequences, range. It's right near the series because it kind of does the similar thing. Now, it basically divides the domain. And it asks you for domain. What our domain? 0 to 1. Let's plug that in. What's the steps? How many steps? By default, I believe 10, right? 10. And by the way, the actual domain is by default 0 to 1. So I don't even need to plug it anywhere. It gives me the set of numbers. You see, the numbers are uniform. 0, 0.1, 0.2, 0.3, 0.4, and so on and so forth. I mean, uniform distribution from 0 to 1. Like, where is the start? Start is here. This is the 0 point, and this is the last point, right? And if I will take all of these parameters as my sampling rate and plug them in, you're going to see that I have amount of points distributed along the uniformly parameterized curve. Does this distribution looks uniform to you? No. And it's supposed to be like that. That's a NURBS curve. And if I will increase the, instead of a domain will be divided by, let's say, 20 steps, right? Or maybe even more, you're going to see that it's really pinchy here. The distances are different. What are we going to do about that, and why they're different? Well, they're different because of the nature of the basis functions and the way how we calculate the curves as well as the surfaces. We already talked about that. Can we make it more uniform? Is it even possible? Well, the answer is yes, and that's where spans come into the play, because spans, I'll remind you, they are the sections defined by the vector nodes parametrically on a curve, which defines the ability to influence every single point and what kind of a range it has the most effect, right? So if I will divide this curve by many spans, and every single one of them has a very limited section of a polynomial which describes our curve, like for example in the power of 3, or basis function in the power of 3, meaning that 3 degrees per segment, then we have a much more uniform distribution. And we can actually do that. So if I will take this curve, Control C or Control V, like move it around here, right? And then I will go in and I will type in Rhino, rebuild. As you're going to see now, the parameters here you probably have different. This is my parameters. So as you're going to see, the representations of the curves and the way how you reconstruct them and construct them are different from system to system. If it is an A-class system, it will give you an ability to specify amount of degrees, amount of spans, right? If this is a more generalized software like Rhino, it's actually can't specify amount of spans. You can figure out how many of them will be by using division. You have the point count, amount of control points, and amount degrees per this bench, right? How many of them will be in a segment, and through that can figure out how many spans they are, and it actually can tell you that they are indeed 6. So the distribution like this gives us a lot of control points, and they will be split in the segments by 3 degrees. So 3 degree segments, okay? And it basically, the distribution of control points, even though that it's not uniform, distribution of spans for the uniform curve is uniform. So we'll have the proper uniform distribution and much more control over the curve. It become to be more uniformly distributed. So if I'll click OK, and we'll construct this curve, it's going to see this curve, so not this one. Let me take the original one. This was the original one, that was the new one. You're going to see that, oh boy, yeah, that's a much more complex curve. If I will plug that in instead, and I will create set1 curve, look at the distributions now. You see how much more uniformly distributed, right? Now I'll remind you, let's go back to the top view. Let's go to the top view, right? Okay, let me just kind of plug it here. So that was the original one, that was the reconstructed one, right? So let me go into the surface again, surface. Oh, sorry, surface, curve. Curve, right click, set one curve, specify the curve, reparameterize, right? And let's just also try there. You're gonna see how it was, piling up in the point of extreme tension, where there is just not enough of a lead-in, and all of the points are really aggressive, and more uniform distribution of the same curve, which looks like this. Now, of course, the curve is not the same. It's a different curve. And if we talk about the A-class modeling, sculpting, this, what we did, basically separated it on a lot of spans, is a big no-no. We don't do that. But for different reasons. This lesson is not about an A-class or not about an alias or something. This is about parametric design. And in parametric design, we do that. And we do it a lot to create more uniform distribution of control points within our domains. So this is a very handy situation. Now, I need to mention that you can't construct perfectly uniform reparameterization or reconstruction of a curve or a surface. mathematically speaking, for a curved geometry, a NURBS curve geometry, it's not really possible, but we can get close, right? So when we're reparameterizing, the more and more and more control points we throw in, the more spans we get in return. Once again, a Rhino will do it automatically. The more uniform distribution we will get. It never will be perfectly uniform, but close to that. Okay, so as we can do it in the curves, of course we can do it in the surfaces, because the surfaces are relying on the NURBS curves, right? We already talked about that before. So what we're gonna do, we'll go back to our perspective mode. Once again, I'm double-clicking, double-click, double-click, in case you forgot. Right, let me just delete this crap. Let me delete this section as well, and focus on our surface, these ones. So what I'm gonna do, Control-C, Control-V, put it aside, right? This is our surface, a new surface. And then what we're gonna do, we will reparameterize that, not reparameterize that, we will do it a little bit later. We will reconstruct the curve. So, surface. So I will type rebuild, and this time for the surface. And as you can see, now we have not only U, but U and V, point count, and the amount of degrees. I will stay the same, and you're gonna see we have a span counts for these for the surface. So the surface we will get, right? So I'll click OK. And as you're gonna see, we have quite a lot of spans. Let me take the original one and just delete that. This is the new one. And I will go in and just duplicate, set one surface, click on this one and toss it here. Look at the distribution. So between these one and these one, let me just, I don't know, let's take this view, right? Swap it in. You see how cramped it is, how much less tension it has right now, right? The more we reparameterize, the more spans we do, the more uniform the distribution will be. Never will be perfectly uniform on a curved surface, but more and more and more evenly distributed, right? So if I will get even more reparameterization, it will be more uniform, and so on and so forth. Okay, what's next? Now, next, of course, the domains. And even though the domains are correct, so I mean, it's wrapping around, so the length is on U is correct to describe the whole length of the surface, it doesn't mean that the aspect ratio is correct, right? We already talked this through, that we can change parametric domains over surfaces and curves in Rhino directly, specifying correct or very specific parameters. In Grasshopper, we have only an option to reparameterize between 0 and 1. I hope you already remember that. So how are we going to reparameterize that in Rhino? Just basically tossing up the surface with a very specific domains. Like right now it is from 0 to 294.17 and 0 to 76.323. I don't even know is it really correct or not, right? So what I'm going to do, I will take the surface. Let me isolate that. I will type isolate and click on this icon on Grasshopper, which basically hides what Grasshopper does, right? Now I'll select this surface and I will type extract isocurve. Now it asks me which one. I can say all. I need one somewhere in the middle. This is the flat. So this is basically the geometry which doesn't have curvature along the V direction, right? So I can pick it any, like for example here, right? Hit enter, and let me do another one. So I will go in and I will type extract isocurve, but this time it will be on V direction. I'll click on V, right? And I'm gonna place it somewhere. Let's say here. It doesn't matter, right? So I have two curves. They are curves on surfaces. They are representing with a specific tolerance the geometry of our surface, right? So if I'll select them, like for example this one, and I will type length, it gives me the length of a surface. So on U direction it is, let me just represent, just type it here, 185.12. I'm looking here in the console, right? Okay, what's about this one? Let's create the, come on, where's my curve? Oh, this one. So the curve length, it gives me the value 76.32. Let's type it, 76.32. Okay. All right. what is the aspect ratio between these numbers? What is the aspect ratio of our surface, right? A relationship between U and V. Well, let's use the calculator and figure it out. So 185 divided by 76. And we get ourselves like 2.43. So it will be, oh, 2.43, yeah. So it will be 2.4321, right? Makes sense? Now, we can take these numbers, or even these numbers, and reparameterize this surface. Now, what is the current domain? This one. What's about this aspect ratio? Maybe it is correct. We don't know. Let's figure it out. Let's type 294. Oh, sorry. 294 divided by 76. And we have the aspect ratio of 3.86. Doesn't look like it is an aspect ratio, isn't it? What numbers the Rhino actually brought in here, what kind of a compensations he did to get these numbers, we don't know. Well, at least I don't know. They never specified that. And I mentioned in the previous lesson, depends on the curves. It can be an arc length. It can be the quarter length between control points. It can be the actual length of a curve. And for the surfaces, there are even more options. So I can't be safe to predict specific results here and there. But I see that this is not the proper aspect ratio of our surface. But kind of relatively close to that, so maybe this is the issue. So what I'm going to do, I will delete these curves. I don't need them anymore. I will select on my surface, and then I will reparameterize that. And I will see what kind of options for reparameterizations Rhino can give me, and will they help me. So I will, when surface is selected, type Reparameterize, like this. And you're going to see it starts, okay, U domain starts with 0. Are you okay with that? Will it be with 0? Like, yeah, 0. The U end domain will be 294. But this is the current one. I don't want that. So if I will say 294, it will be 294. But I don't want that, right? So the end of a U domain, I would like to be like this number or the actual aspect ratio. And I will type then U domain 2.43 and hit enter. All right, now it starts for the V domain. Okay, V domain starts with 0. Am I okay with that? Yes, I am. It will be 0. Yeah, good. What's the end of the domain? Not the current one, not 76.3, no, this one, right? But it will be 1, and I hit enter, right? So now we have a new domain. You're going to see here that it's automatically, because the surface is linked, it automatically reparameterized that. And this has become to be our original one. We're going to convert it to 0 to 1, and our script does this, but this is what we are working right now, right? So if I will now turn the geometry on and look at the representation of the hexagons, it becomes to be more uniformly vertically and horizontally here, especially you're going to see this. And that's because we have a better representation of the surface in terms of its aspect ratio. And as we are working with the hexagons and want to maintain our aspect ratio as much as possible, that's the solution. Okay, what else could we do to make it more uniform? Well, we can just divide it even more. So I will go in and I will type rebuild again. And this time, let's say it will be 80, not 800, 80 by 80. There is, of course, a limit of how much it can carry in terms of like the actual results, right? But here we go. And this is the new surface. So let's take the this one and let it be. Let's take this one and say set one surface. And look at this. And you're going to see the difference, especially when the pinching happens like this. You see how much wider it become, how it much more uniformly become, right? These ones. So if I will take that back to this surface, it becomes to be a little bit more squashed. And the more and more we do it, I don't know, it probably will be a little bit different to see, but let me just kind of take these ones, set one surface. Let's go maybe to the front view. It's difficult to spot. Let's say like this. We're looking at I don't know, this one, for example, right? actually, actually, it's quite similar. Just a little bit differently, but at some point, you know, the additional separations will not give you much of a difference. But anyway, that's definitely helps, especially if you compare it with the original one. Where was the original one? This one. Let me just kind of plug it into the original one. Yeah, you're gonna see the difference, right? All right, so these out of the way. Let me take this one. Oh, this one doesn't matter. Let's just delete this. I will show myself everything. Let's delete this one. Let's delete the curve and delete the surfaces. Now, we already talked about the fact that these hexagons are now goes beyond the v direction, right? And it makes a lot of sense because the actual pattern tries to maintain aspect ratio and it's already rectangular. But that's where the different modes can come into the play. Now, of course, we will be able to sort all of them later for the next stages and we're going to chop them off. But I just want to show you another mode. Like, for example, instead of anisotropic flat top, I will switch to isotropic flat top, for example, right? And of course, I will change the mode to stretch. You're going to see now it's stretched, right? If I will change the, let's say the amount of elements here, like this, right? Yeah, maybe even more. And we have an issue with the stitching. Let me hide this for now. Let's look. Okay, 40. Bam, 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 bam. Okay, cool. And let me maybe do it like this. So you're going to see that when it tries to stretch, for example, on U direction, it perfectly stretches. V direction kind of goes to the ends, but not quite. You're going to see here, there is just no pattern anymore. There's nothing else. And that's where the additional options for our point construction comes into the play. You're going to see that I can add more and completely cover in both directions, in U, in V, on both, to to have a fully enclosed hexagons, even if they are just barely touching the surface, right? So this is another good feature. And we, of course, capitalize on that a little bit later. So what I want to say is that it works every mode here, except of the scale, for obvious reasons, will work with the closed geometry. So the closed geometry switch is right there. Okay, last but not least, let's talk about the open surfaces, but not planar, right? Let's do something which is not planar instead of this one, right? And show you another few nuances. So imagine that I have some kind of a skewed surface, right? Let me type rebuild, and I will rebuild it to something meaningful, like 3x3. No, let's go to 4x4, like this. Select the surface, not the original one, the new one. Hit F10. Oh, I actually deleted the new one. Okay, never mind. Okay. All right, here it is. So I made it a little bit more complex, so we'll have an option to bend it a little bit in the different directions, right? So why not? Let's bend these one. Let's bend these one. Like kind of like just do some random modification. So we will see that the surface indeed is not planar. It's actually can be quite complex. Maybe it has really aggressive pinches like this, because why not? You never know what life throws at you, right? So like this, like an okay, I believe this is pretty aggressive bend on already, right? Very bendy surface, right? I'm just gonna take maybe this one indeed. Come on, it's over here. Okay, that's enough. So let's bring the surface in. You already know what to do. Surface, right click, set one surface, click on the surface, and now let's plug that in, right? Let me delete all of these ones. Right, so this is our surface. It has some domain, right? I don't know which one. Well, I know which one. It's this one. I don't know is it a correct domain or not, we will figure that out. Now you're going to see these kind of lines because the pattern works with the closed structure type. It tries to close itself. It can't, of course, so hit open. This is the open geometry. I will hit F11 to remove control points. And we have our pattern, right? Now, which one direction is U and which one is V? Let's figure out. So this is the U direction, this is the V direction. Okay, it's not going to an end. That's probably because we don't have the proper amount of points. Okay, now it does. And let's say that we will use the anisotropic mode to maintain proportions as much as we can. So the amount of the division is supposed to be identical, of course, to make the proper distribution. Let's go in and check that it is U anisotropic. Here it is. Look at that. Now let's go in and probably change the size a little bit. Let's say 30 by 30. Will it work? No. 29, 28. Okay, 28 will work. 28. All right, that's good. Good example. Now, look at what's going on. You're going to see when the surface is curved, all the points which are trying to match its proportions, right? Because this was the U direction, right? And this one was the V direction. Everything in V directions tries to follow, but it follows on a surface. Surface is bent, it's twisted in all directions. It has different curvature everywhere. It's just completely distorted. And the curves the points they tries to follow because they are mapped on the surface. Their domain is exceeding the surface, meaning that there's no actual surface, but through the curvature extension, system can predict where the surface will go, and this is how the surface will actually wrap on itself if we will extend it as a surface. And the curve the point starts to follow. That's why they bend around. On top of that, you will notice that even though that we try to do our best to maintain proportions of our hexagons, you're going to see this is, let me just kind of hide this. You're going to see not quite, you know, this one is bigger, this one is smaller, this one is smaller, it kind of shrunks on this side. Why? What's going on? Where we made a mistake? Well, honestly, there's no mistake. There's no mistake because that's the nature of mathematics, because the surface itself is bent in 3D space, and it's bent really aggressively in all directions, completely destroyed actually. And because the surface is bent and the actual pattern, the hexagonal pattern, is very demanding in terms of the actual positions of points, very specific ratio between them, the 3D surface just can't accommodate for that. If the surface is bent, it naturally bends everything which sits on it, right? So when you have distortions of this nature, this is absolutely normal if your surface is, well, distorted. So this is not an error, or this is not an issue. In fact, the script works as it's supposed to work. It tries to cover it, it tries to maintain proportions as much as it can. And in this case, we did almost everything. Now, of course, the aspect ratio may be different a little bit, so we're gonna, of course, try to do that. So we'll type rebuild, and when we're rebuilding, I believe it will automatically, let's say 40 by 40. Once again, we're increasing the density, so it will be more uniform. And as I said before, it always has some limit, never will be completely uniform, right? Hit OK. Now we reparameterize that. We don't see a lot of a really difference, maybe just a very minor one. And then let's try to reparameterize. And this time I will try to rely on the, so one second. Oh, of course, I forgot to replace the surface. So this one we will, the original one, I will just delete. And this one I will reassign, right? Now, right now, we definitely see the difference. The difference happens. It's more uniformly distributed. Okay, that's good. And last but not least, reparameterization. So reparameterize. I will try to see what automatic mode will give me. So start, automatic, and it reconstructed the domain. I believe it is reconstructed the domain. Actually, I never spotted. Let me try again. So, surface, set one surface, 072 by 64. No, we didn't reparameterize domain, right? But probably it will not give us a lot of our differences. It still will be skewed. And on top of that, you're going to see when you try to find the aspect ratio, you're going to see that the aspect ratio will be different, depends on where you measure it, right? So you can measure these line, try to take the average, then try to sum these lines, try to take the average of them and calculate it. It will be very specific aspect ratio, but not exact because surface is bent in 3D. So in this case, I would say just reparameterize, set automatic, and in this case it probably will be one of the best solutions. But of course we can always do it manually. In the future examples we will do it manually as well. All right, so that's how you map the single surface with the current pattern. Once again, we have a few modes. Let me actually show you before the end the last mode. The last mode is the scale. So let's go in and change this to scale. And you can see the scale does as you think it is. It just scales on a surface, right? Scales on a surface, and that's where the rotation actually comes into the play, because you're going to rotate that if you wanted to on your surface the way you want, right? And you're going to see that it still will bend and distort even the scaled one, because the surface is bending and distorting, right? It just follows the surface, right? Okay. And just remind you that you can rotate, of course, in the different modes, like your anisotropic. Here we go. We're going to rotate. If we want to do so, we can. Here we go. It tries to rotate, and it is rotating indeed. All right. So all the modes are working. We know how to map on a single surface, on flat one, on distorted curved one. We already figured out that our script indeed works, and works very nicely with closed geometry. So we're going to construct a closed geometry and will bite its tail in all the modes. So in this regard, this is all nice. Script actually ready for the next stage. What is the next stage? The next stage is, well, what we actually need the most. An ability to construct pattern not across a single surface, because honestly that's not really very beneficial in real life scenarios, but across multiple surfaces which are connected together, like a B-reps or poly surfaces, well, your actual geometry. It will be a pretty tricky part, but trust me, we already did more than half. So at this point, it's more than 50% done. The next part is tricky, but not really that long. So we're actually progressing, and sooner than later, you will see the end of the tunnel, and you see how the script actually works on your B-reps. Yes. All right, guys. Thank you very much for watching, and I will see you in the next one.